Good evening, welcome again. Today, we're gonna continue what we started, or go at least, go back to HCS12 after what we did in the last week lectures, last 2 or 3 lectures in talking about software design, embedded software design, requirements engineering, types of requirements, how to specify requirements, and using different methods, text or visual, and we did a model-based example using MATLAB Simulink and AutoCode generated code, embedded software code from requirements specified with model-based using MATLAB Simulink. Today we're going back to cover what we still didn't cover. Yeah, some of the things here, مثلا math, we already covered some of the stuff. Even the multiplication, for example, division. I did them in the class demos in the flipped classroom, but I'm here today to systematically go over them and other stuff. So a lot of them, loops, branching, we already used them, but to check, final check on anything if we missed. For those who came late, Wednesday, our class is going to start at 3:30 p.m. Okay, so software development, we said before you start writing your code, you should present or design the software. One of the methods we specified here in this presentation, it is uploaded to e-learning. So either using flowcharts, model-based, text, etc. And these are a lot of examples. And here he said use like steps text to do something, then wrote the program to add contents of memory and store the result somewhere. Here, another program that used a flowchart to then generate the program. And to remind you, we wrote more complex examples here in the class demos that I covered in the flipped classroom. If you didn't, I expect that everybody has watched those classes and looked at the developed software. And if you have any questions, I'm expecting you to ask about them. And we stopped here last time, or when we were in this topic. The carry flag, we talked about the carry flag that is a bit part of a register called the condition code register, the CCR register. The carry flag is set or reset based on the instruction, the last instruction that affects it. For example, an add instruction, the result of it, if you go to the data sheet and we check that in the data sheet, that it affects the carry flag and it has a triangle under it, right? Which means it affects the carry flag. So the carry, if a result from adding 2 instructions will result in a carry, the carry flag will raise, it will become a 1. If it doesn't result with a carry, the carry flag will reset, become a 0. Same with borrow. If you borrow, the flag is raised. If you don't borrow, the flag is reset. Okay. This is useful, and we used it when we added 32-bit with 32-bit, if you remember, right? Adding a number that results in a carry, this carry should be added to the following 2 numbers that are part of the bigger number. And we did it in an example. And I think this program does something similar, adding 4-byte numbers. We did that in the flipped classroom. And here they're adding the carry bit in the 2nd byte, 3rd byte, right? Well, 3rd and 4th byte, because the first 2 bytes are 16-bit. You can use add D, but add with carry has to be with add with carry A and add with carry B. So you do them in the 3rd and 4th byte. More examples, you can go over them. The Bcd number example, I did it for you guys in the flipped classroom. Is there, you have the code and the explanation, me writing the code live with you so you can watch it if you have any questions. I didn't mention in there the DAA instruction, the DAA instruction. In BCD numbers are binary coded decimal numbers, right? So the decimal numbers from 0 to 9 are binary coded using the bits 000, 0001 down to what? 1001, right? 9. So when you do a BCD operation, any result or any resulting number from any kind of operation has to be in the range from 0 to 9, yani from 000 to 1001. Okay, what happens if you add two numbers like مثلا like 1000 yani 8 plus 3 0 0 1 1, the result is what? 1 1 0 1, and this is what? This is C D, huh? This is
C.
B. This A B. This is B. B, right? B is not here. B yani, comes after the 9. So we need to be in, and if you convert it to decimal, is equivalent to what?
11.
9, then A, B, right? So yani 10, 10, 11. So this is equivalent to 11. How do I convert the B to 11? If you add the 6 to it, B plus 6 is what? B yani B is 1 plus 6 is, which is 1 0 1 1 plus 1 0 1 1 0 is 1 1 0 is 6, right? 4 plus 2. So it will become a 1 0 1 0 1 0 1, which is 1, right? So the B will become a 1. And the 1 carry, you add it, if you have zeros here, 1 plus zeros is 1, right? So 1 0 0 0 1 0 0 0, yani what? 1 1. Okay. So the result, so after this, if you add a 6, you get the 11, right? Instead of doing this, adding the 6, you can use the instruction DAA. DAA will adjust the last result in the accumulator by adding 6 to it. Okay. Yani, instead of you adding a 6 by yourself. Why 6? Because the numbers after 9, A, B, C, D, E, F, then you go back to 0. You roll over back to 0, right? Multiplication and division, we covered them. I covered them in the two flipped classrooms. The extended extended multiplies two 16-bit numbers, have to be in this register. The result is stored here, and so on. For unsigned numbers, multiplication. For signed numbers, 8-bit signed numbers multiply. Extended division, 32 by 16 for unsigned, for signed. Fractional division, unsigned, integer division, signed, 16 by 16 division. A lot of examples, you can go over them, but we used some of these instructions in our flipped classes. Convert a number to BCD, then BCD to ASCII. I did this in the flipped class. Using different If you compare the codes, I don't know, some of the things may look the same. Okay, I'm moving faster as you guys are experts in assembly. Program loops, even this, see, we spent a little time back then. Now we're moving faster because we did a lot of these things. Program loops, we did the delay loop, right? When we blinked the LEDs. When we blinked the LEDs by turning port H on, doing a 500 millisecond delay, then off, then delay, right? The delay was a group of instructions repeated over and over again in a loop. Loop statements in C are do, check condition forever. If the condition is true, you go here. If you're not, you go out. For loops, we're all familiar with for loops, counting up or counting down. While a condition is true, do this or not. Repeat something until a condition is not true. These are all types of these are trivial now kinds of loops. مثلا for loop I n equals n1 to n2, do this. So you initialize I with the initial value, you check it. If reached the final value, you exit the loop. If not, you go do the thing, increment the counter, and keep doing this forever, right? How do we do this in assembly? You compare this with this and branch if not equal to somewhere where the no is, else you don't branch, you keep going. And here you have, after the increment, a branch forever to here. When you do branching, so to do loops, you need to be able to branch. When you do branching, you need things to compare if true or not, right? One of the things we compare are the flags in the condition code register in the CCR register. So you can use the carry flag, right? And all these shaded flags are things that you can use to branch. The unshaded are are not used for branching, for interrupts, external interrupts, etc. So the carry flag, you can branch if there is a carry or not. You can branch if there is an overflow or not. You can branch if the result is 0 or not, and so on. Okay. So if you classify branch instructions, first there are unary or unconditional branch instructions that always execute, like the instruction we use in our code, branch to forever, right? You always branch. You don't check for a condition to be true or not. Simple branches, branches that check for a bit in the CCR register. Branch if carry, branch if overflow, branch if negative. Okay. Unsigned branches. Branches are taken when a comparison or test number results in a specific combination of CCR bits. Combination, multiple bits are affected. Signed branches, we're going to look at specific instructions in the table. Signed branches, check the sign bit, which is the n bit. Okay. From the how far you can branch point of view, there are short branches and long branches. Short branches can send the program. When you branch, when I talk about branching, we're talking about a program counter pointing to a memory location in the program memory with an instruction, مثلا, okay? And you branch, مثلا, 10 locations before or 10 locations after, okay? Now, if you branch up to minus 28 locations before, and in negative, up to 127 after, this is called a short branch, and you use branch instructions for it. We call it a branch. If you want to branch anything further than 127 or 128 in the minus, within the 64K range of the page, we call them long branches, and we use jump instructions for those. Jump. Okay, we'll look at them. So here is a table with a lot of branch instructions. Unary, that always happen, branch to a memory location. A long branch, L branch, is the one here that branches us the jump, that can send us more further than 128 locations. The branch, see the location is 8-bit, so within -28 to 127. This is 16-bit, which means that we can branch within the 64K. Okay, branch or branch, BRN. Branch never. This is branch never. This will not ever cause a branch. Okay. Simple branches like branch of carry, clear. Branch of carry, flag, set. Okay. Clear yani 0, set is 1. Branch if equal. Equal yani, usually you use this instruction, branch if equal, after مثلا a subtract instruction, or an addition instruction, or a compare instruction. These three instructions, after you subtract two numbers or add them or compare them, compare yani it subtracts but without saving the result. Most yani subtract and compare are the most common. After you subtract two numbers and the result is 0, the carry flag, the 0 flag is raised, right? The Z flag becomes a 1. So you say, so if you want to keep the result after subtracting, you subtract. If you just want to check them if they're equal, you compare them. Okay, say compare A with B. Okay, then this does a subtraction. If they're equal, the 0 flag will become 1. So the condition will be true, and you can branch to somewhere if this condition is true. Else you continue to do things if the condition is not true. Same for long. Branch if minus. It checks for the negative flag, if it is 1 or not. Okay. Branch if not equal, it branches if the 0 flag is 0, not 1. يعني عكس be equal. Branch if plus, as opposed to the negative or minus. Branch of if overflow flag clear, branch if overflow flag is set. These are branch instructions, simple ones that are based on checking CCR flags. Unsigned branches, and I forgot, I gave you, I don't know, no, I didn't give you. Unsigned branches and signed branches. When you want to compare numbers here, branch if higher, if a number is higher than another number. Branch if higher or same. Branch if lower, branch of lower or same. So when you compare numbers unsigned, you check if they're higher or lower than each other. And if 0xff, if you compare 0xff with 0x 0f, what is higher? The first one is higher, right?
Yes.
1 is higher than 2. But if you use this one, branch if greater, this is greater. Why? Because here we're dealing with signed numbers. The most significant bit, and if you represent this number, this is a 1111 1111. This is a negative number, while this one is a 1111 0000. Okay, this is a positive number, right? This is a -1 if you use the 2's complement, and this is a positive f, right? يعني 16. So this is greater. تمام? So you branch of greater, you branch of higher. So same thing, greater, greater than or equal, branch of less or equal. Say you use
دكتور في مجال تعيدها.
بعيدها. Okay. One is a greater than -3, صح؟ greater لأنهم signed numbers. One is 0 0 0 1. The minus 3, what is a minus 3 in binary? What is a minus 3 in binary? You take the 2's complement of 3, right?
1 1 0 1.
1 0 1 1, right? Right? This is 3. This is minus 3. The 2's complement. Yeah, you flip it all bits and add the 1. Right? Flip all bits. Add 1. Right? Minus 3. 1 is greater than 1 1 0 1. However, if we're talking about higher, and this is for signed numbers. For unsigned numbers, unsigned numbers, 0 0 0 1 comes before 1 1 0 1. In unsigned numbers, this is a what? This is a 1, and this is a what? F plus 3. Huh? No, unsigned. Yani this is a 1 2 4 8. This is a 12. 8 plus 4, 12, 13. Right? So 1 is lower than 13. If you count, it becomes before. Okay? So if you're dealing with signed numbers, yeah, Yazid, and you want to compare between signed numbers, you use greater and less. If you want to compare between unsigned numbers, you use higher and lower. Clear?
Clear, دكتور. تمام.
Okay. طيب, compare and test instructions. These are instructions that we usually use before we check for a condition. So if you want to compare two numbers, if A greater than B, do this, right? Else do this. And most of our conditions that we use, if this is equal to 0, do this or not. If this is greater than this, do this or not. How do we check greater? How do we check higher? It all relies on the flags, right? When you want to say branch if greater or equal, you're checking for two numbers that you compare, that it takes the negative XORed with the overflow flag. If this result is is 0, the condition is true, else it's not true. If you want to compare numbers, if they're equal or not, you can just check for the 0 flag. If it is 1 or 0, after you subtract them from each other, okay, you compare them. So all these instructions, okay, you have to affect the flags first, then use them. How do you affect the flags? You do a comparison. So you bring the first operand and compare it with the second operand. For example, compare B with A. Then, if you compare B with A, and then go use, for example, this instruction, branch if higher, okay, B with A, B will subtract, B will be subtracted from A. So this, if A was higher than B, the condition will be true. Else, it will not be true, okay? So you compare, then you say CBA, then you say branch if higher, BHI, okay, to somewhere. So every branch here shall be used after a comparison instruction that compares the two operands that you want to make the decision based on them. So the compare instruction, يعني, طيب, can I use subtract B from A? Yes, I can, but the subtract will result in a result of subtraction and store it somewhere. You don't care about the result. You want to check them against each other, if they're equal or not, if one of them is greater than another or not. Compare A with an operand in memory. Compare B with an operand in memory. Compare D with an operand in memory. Compare S, all these registers, you compare them. Okay? The test instruction, you compare with a 0. The test instruction, you compare, instead of saying, so TST operand, okay? You subtract a 0 from a number. طيب. If you after it you use مثلا branch if greater, branch if greater, BGT. So if m is greater than 0, يعني positive, you'll do a branch. It will be true. If m was less than 0, this will not result in a branch. You continue. يعني false. Okay. If you want to check if the operand is 0, you say but branch if equal, this one, or greater or equal, or if you want it equal لحالها, branch of equal, BEQ. BEQ. It will check for the Z flag alone. So it will subtract a number from a 0 from a number. Okay, if you subtract 0 minus 0, the result is 0, the flag will raise. Okay, otherwise it won't raise. Test A, you test A against 0. So you subtract the 0 from A or B. And to test if A is a 0 or not, right? Or minus or positive. Okay. So you compare or test, then you use a branch instruction. Now, these instructions here, we use them in one of our class demos. You decrement and branch of equal. You decrement a counter, مثلا هون. You decrement a counter. You specify the counter, I مثلا. And branch if the counter is equal. Equal to what? Equal to 0. Equal, يعني equal if the 0 flag, you check if 0 flag is 1. When you decrement a number, you subtract a 1 from it. The result will not be a 0 unless you keep decrementing. You become a 1, you decrement 1 minus 1, you become a 0. Then the condition is true, right? So you decrement a counter you specify in memory. If after you decrement the result is a 0, you branch to this relative address here, or you don't branch. Okay. The counter here, sorry, it can't be something in memory. It has to be a register, A, B, D, X, Y, or stack pointer. Decrement and branch if not equal, عكسها. If the 0 flag is not 0, if not 1. Increment and branch if equal. Increment and branch not equal. Test the counter against 0. Okay, if the counter was equal to 0, and here you can have the decrement before it or a subtract before it or whatever. You test the 0 flag. If it equals to 1, you branch or not. Test and branch if not equal. And go back to the flipped class demo class 2, I think, where we did the blinking, and I used one of these instructions and explained how. Okay, having the ability to branch and compare, you can go implement any of those loops you had. And here are a lot of examples. This is an example for a for loop that initializes I to N1 from N1 to N2 to keep doing something. Okay. Okay. 2 memory locations, N1, N2, I. So you initialize it, load it, compare it. If it's equal to N2, you compare it to N2. N2 here is the index, and I, is it equal here or not? If greater, you go you branch if greater to next. Next is here, and you're done with the loop. If not greater, you keep doing S, right? You increment I, branch to loop F, and so on. Count down for I down, while loop, all the same concept. You have to, you do something, you check for a condition, either before or after. Repeat until many examples. I'm moving fast, huh? طيب. I'm going to close this. Now we are here. Bit condition branch instructions. I actually like it. Yani we spent a lot of time before, but we used almost everything. More on branching. By the way, we're almost done with assembly. The next closest program we're going to write together, we're going to start writing C. Even for the lab assignments that I posted today, you are to do the task into using assembly and using C. Then whatever what comes after is going to be in C. طيب, a branch if clear or branch if set. What is clear or set? You have an operand, memory location. You mask it, a mask, to a location. So here, for example, a branch if clear, memory location here, memory location. Let me, what do you like? Let me give you any address, 2000. If the number here is what, مثلا 1 2. If this number 1 2 or 0 0, يعني مثلا, you want to check this if it's clear or not, or part of it is clear. If you want to branch if this is 0 or not, you can just go do test, the one that we just did, right? Test and branch if equal memory location 2000, but here before you need load D immediately with 2000, right? Then you decrement test and branch if equal, طيب, test and branch if equal D comma to you branch if equal to مثلا I don't know, here, and here will be somewhere here مثلا. Okay, but if you want to test a specific bit in the number here, you can mask it. So you can say branch if clear, give it the address where the operand is at, comma, what bit do you want to test? Okay, مثلا هذول 8 bit, right? 8 bit. Assume these are 8 bit coming from 8 push buttons. You want to check one of them only. مثلا 1 2 3 4 1 2 3 4. You want to check this bit only. If this is 0, you want to branch. If it's not, you don't want to branch. So you mask everything. You mask, what do? You AND with 0 0 0 0 1 0 0 0 0. The result will be all zeros, right? Except this bit will depend on this 0. If it was a 0, you'll get a 0. 0 ANDed 1, 0. Else, if 1 and 1, it will be a 1, and the result will be non-zero. So you can mask by you provide the mask here, $, 0 0 0 1 is 8, right? And everything else is zeros. So you branch, here the mask will be $, 0 8, comma, to loop. واضحة هاي يا اخوان ولا اروح على مكان اشرح اكثر؟ So for this branch here in this example, the address 66 in memory is checked. What's in here is checked. What's in here is 8-bit. 1, 2, 3, 4. 1, 2, 3, 4. Then it is ANDed with E0. What is E? 1, 1, 1, 0, 0, 0, 0, 0. So the 3 most significant bits are checked. If they are all ones, يعني واحد منهم 1 or any one of them, 3 bits, all ones. If they are all ones, okay, because you specify the bits you want to check, the condition will be true, and you will the program counter will go to the label where the loop is at. Okay, so this is the mask. The bits, they are masked with zeros, you don't care about. You only check for the bits that are masked with ones. The branch will happen if they are clear. You specified which bits you want to check, the ones you specified ones next to them. If you want to branch, if they're ones, use the other instruction, branch if set, if they are ones. So the branch here will be taken if most significant 3 bits in this memory location are all zeros, because what? I used branch if clear. If I want to branch if they are all ones, what do I use? The branch if set. يزيد.
دكتور معك. تمام دكتور.
Okay. Examples. Okay, some instructions on initializing registers or memory locations. Clear and a memory location. Clear register A, clear register B. Shift and rotate instructions. We have 2 kinds of shift and rotate instructions. First, we start with the shift, then we go to rotate. Shift. Shift instructions, we have arithmetic shifts or logical shifts. Okay, arithmetic, and we have logical. We start with arithmetic. We shift left, register A or B or a memory location, operand. How do we shift? So we say, مثلا, well, let's do memory location 2000. We have memory location 2000. Here we have مثلا 3, 1. And we do arithmetic shift left, memory location 2000. What will happen? The 31 will get replaced with this. 31 is 0011 0001. An arithmetic shift left will bring a 0, replacing the least significant bit. This is the least significant bit. This is the most significant bit. Okay. Insert a 0 here. So a 0 will come in here. The 1 will go to the next location. The 0 will go to the next location. The 0 will go to the next location. The 0 will replace this 1. Sorry, 0, 1, 1, 0. And the last 0 will go to the carry flag, to the carry bit. So 0. So the result will become what? This is a 0010 يعني 2, and this is a what? 0110, which is a 6, a 62. So the 31 will be replaced with 62. And the result, there will be no carry. So if you do this instruction, then you say a branch if equal, will the branch happen or not? No, it will be false. They call it an arithmetic instruction an arithmetic shift, because a shift left is basically in math is what?
ضرب multiply.
Is a multiply by 2, right? So الرقم اللي كان هون was 31. After shifting it left one time, the result is what? 62. So we multiplied this operand by 2, right? Every shift left will do a multiply by 2. If you shift left twice, you multiply by 2, then by 2, and you should multiply by 4, right? And this is really much faster in terms of, if you go check how many clock cycles the arithmetic shift left takes from the CPU, compare it with the multiply instruction, you'll see that this is larger. Okay. And you can even do shift in C, right? This is in assembly, but if you want to do it in C, so if you want to shift X, a number X left, you do X shift left one time, right? So this is equivalent to X equals X times 2, right? Okay. The most significant bit goes to the carry bit, the carry flag. Can we shift 16-bit? Yes, if they are in register D. Same thing. Now for the arithmetic shift right. And this is important. Since it's an arithmetic operation, then the number matters. The number has a value, right? It is a number. It's an arithmetic operation. So a positive number has to stay positive, a negative number has to stay negative, which means that the most significant bit here, you cannot insert a 0. Okay? You have to retain this bit by keeping it as is. So a branch right, a shift right, arithmetic shift right for a 8-bit operand in memory or registers A or B. What we do is, if we have this number 0, 0, 0, 1, 0, 0, 1, 1, what is this? 0x. 0x is زي $, نفس الشيء, okay? 1, 3. If you arithmetic shift right, let me have more space here. So if we have a number 1, 2, 3, 4, 1, 2, 3, 4, we want to do arithmetic shift right for this memory location in memory location 2000. So arithmetic shift right, memory location 2000, and here we have something like 0, 1, 1, 0. في bit ناقص صح? 4 bits. 0, 0, 1, 0. So this number is what? This is a $62, right? So arithmetic shift right means that this bit stays as is, صح? This bit stays as is, and then copied here. This is copied here. This is copied here until we get to the end, right? So this will be a 0, stays as is. Then you shift here to the right. This comes here. The 1 comes here. The 1 comes here. The 0 goes here. 0, 0, 1. The result is what? 3,
51.
1. So we had the 62. The result is 31. And we divided by 2, right? And we kept the sign. The sign was positive. If the number here was a 1, مثلا, this is a negative number. This will stay as a 1 and be copied to here, right? So in arithmetic operations, you have to retain the sign. So you don't shift a 0 in. In the left, it's okay, but in the right, it's not okay because the most significant bit is the sign. And the least significant bit that shifted out here, goes to the carry. If you had a 0, so in our case, the bit was 0, so the carry will, after this operation, will be 0. Now, logical shift. In logical shift, you don't care about the sign bit, the most significant bit. So the logical shift left, you bring a 0 into the least significant bit. Every bit moves one step forward. The most significant bit goes to the carry flag. So for the logical shift left, it is almost the same or exactly the same as an arithmetic shift left, right? Same. You can do it for 16-bit in D. The difference between the arithmetic and the logical shifts is the right operation. In the right operation, you can bring a 0 to the most significant bit, okay? In the logical, in the arithmetic, you had to bring in what the sign bit was. You had to retain the sign. Here, you can bring a 0 in, okay? That was about the shift. Now, we're talking about the rotate instructions, rotate. Rotate instructions, you pretend like that the carry bit now is the 9th bit of the register or the operand you're working on. So it becomes like the 9th bit. So if you rotate left for a memory location or the 2 registers, A or B, the carry will come in replacing least significant bit. The bit 0 goes replaces bit 1. Bit 1 goes to bit 2. Bit 3, most significant bit 7 goes back to carry. Okay, this is the rotate right. So it's like, and I think, it's like a rotate right or shift right through carry. Sometimes in other processes they call it. The carry becomes part of the bits involved in the rotation. Rotate right, same thing. The least significant bit goes to the carry bit goes to the most significant bit, and so on. Easier. Some examples. Original number, you perform the arithmetic shift left here on the number. What happens? Arithmetic, you bring a 0, every bit moves one step forward to the left, most significant bit goes to the carry. A here was a number, now it's a different number. Multiplied by 2, the carry bit is 1 because the most significant bit is 1. There's another. This is an arithmetic shift right. See, you kept the sign bit, and what was here starts shifting. More examples. More examples. Write a program to count the number of zeros in the 16-bit number stored at on. And without looking here, what would you do to count the number of zeros in a 16-bit number in memory?
بدنا نعمل ماسك فاليو بالزيروز كلير اف ست اف كلير
ماسك
اللي هي عشان تشوف كم في زيرو في النمبر.
يعني you mean the mask instructions we just saw here, this instruction, the branch of clear, and you use a mask, or you want to do and or mask bits in a loop?
دكتور بستخدم روتيت وبصير اشيك على الكاري فلاج اذا كان عندي زيرو او لا، وبعدين بعمل كاونتر يعدل لي.
That's a way to do, Muhammad. What Salah mentioned is also true. Salah, and you can do a loop. You and all the bits with all zeros except the most significant bit is with a 1. If, and then you test if it's true, you go somewhere, increase the counter, else you go, and the other bits all with zeros except for the one bit number 6, and so on. You repeat something 8 times, right? But it's going to cost you a lot. Yani, it is going to cost you, and it's going to be a long program. What Muhammad mentioned is that we can shift or rotate or shift even to affect the carry flag. If you bring this 16-bit number to register D, 16-bit number, load it to register D, right? Then start doing with an logical shift right for D, right? Or arithmetic or logical or whatever, right? Whatever is here is going to go to the carry, right? طيب. So do it 16 times. 16 times. يعني shift right, branch if carry to somewhere you increment the counter, then decrement the 16-bit counter and go do this again. Shift right, branch if there is a carry, increment the counter, do it 16 times, right? Your original number will stay in memory, and D is just a temporary placeholder. Okay, yeah, Shadi, yes, you want to say something?
مش ممكن نستخدم، مش متأكد، بس مش ممكن نستخدم مثلا XOR مثلا مع الزيروز مثلا ونعيد، ما هو إذا كان على الونز مع رقم ثاني ولا لا؟
True, but how many times you're going to do it? So to check one bit if it's a 0 or not, you need to do an XOR, right?
Yes.
طيب, then the next bit, another XOR with a different number. That is hard to do it in a single loop. In a loop, it's a single instruction. Diamond, the number you're going to do an XOR with or an AND with is going to be different than the one you used before. So you're going to do something 16 times repeatedly. This rotate or shift thing, you can do one instruction repeated 16 times, right? It's all, every time it's a shift. Every time it's a shift. You check the carry flag.
تمام.
طيب, shifting multi-byte numbers. طيب, we saw that you can shift 8-bit number or 16-bit number. طيب, what about a 32-bit number? Something to think about. Look at it here. When you shift it the first time, the most significant bit, and if you want to shift left, 32-bit, shift the lower byte. And if I have 32-bit number here that start at address 2000, 2001, 2002, and 2003. This is a number 1, 2, 3, 4, 5, 6, 7, 8, and you want to shift this number 1, 2, 3, 4, 5, 6, 7, 8. How do you shift this number? And multiply it by 2. Shift the arithmetic shift left. We can do this as a shift. First bit, the most significant, or the least, or the most. Okay. To the left one time, right? The most significant bit of this number will go to the carry. Then you can go rotate left, right? Rotate left. So the carry will jump in here, right? Then a rotate here, then a rotate here, right? Because the bit that goes out of here, you want it to come in here. So send it to the carry flag, then bring it from the carry flag. So if you do for the first instruction, let's talk about left shift, logical arithmetic shift left, the first operand, right? The most significant bit went to the carry. Now you can do a rotate left for the second operand. So the carry bit that came out from the shift will come into this byte, the bit, every bit shift left, the most significant bit goes to the carry. Then you go rotate the other byte, right? Then you go rotate left operand to 0, 0, 2. And if we want to do it real quick, arithmetic shift left, and if for the locations here, it is like this. And you want to shift this left, and we do arithmetic shift left for address 2003, then rotate left 2002, then rotate left 2001, right? Then rotate left 2000. صح؟ كأنك عملت shift the 32 bit. Okay, and this is a code to do it. Here. Boolean logical instructions. Okay, and I think, are we all good? Anybody missing anything? We're almost done with assembly. Boolean logic instructions. Guys, I'm asking if anybody has a question, please stop me. So logical instructions, and or XOR, right? So and register A with an operand, and register B with an operand, and the CC register with an operand. Why do you want to AND? To mask, صح, basically. If you want to set or to clear a group of bits in memory location, I told you مثلا port A is port A, sorry, port A. I have a CPU here, a microcontroller. I have a microcontroller unit here, HCS12 microcontroller unit. I have port A 1, 2, 3, 4, 1, 2, 3, 4. So this is port A 0, port A 1, port A 2, until port A 7. And in here we have a set of LEDs. Okay. And I told you I want all the LEDs on, all are on, all LEDs on. Go turn off LED. If we start from 0, LEDs 0, 0 and 3. What do? You can and is it can we AND an operand, or is it has to be a register? You can. So you can go AND. We know port A is at address 0. So you can AND port A if it is in the directive port A equates 0, 0, 0, 0. So you can AND port A with what? I want to turn off LED 0 and 3. So 0, sorry, 0, 1, 2, 3. So you can AND port A with the 0, 9, right? This will keep you're ANDing everything with 0. Anything you AND it, oh sorry, you AND relax. You AND 0, 1, 1, 0, 1, 1, 1, 1. So you AND with F6, sorry, $sign F6. So when you AND anything with 1 stays as is, anything with 0, you clear it, you turn it off, right? So we masked basically here, we say we masked bits 3 and 0. طيب. And A and B. What did I do? What happened here? Why did this close? And A. And A. It's not like this. You and A with port A. For this, you load A, accumulator A, immediately with $F6. ماشي مش هي. You load A with the mask, then you AND it with the memory location. طيب. So AND is to turn, you AND things with 0 to turn them off. You OR things with ones to turn them on, right? And axial AND, you can use them for axial AND. You can use it to AND with condition code register bits. You can AND or, and to set or to reset, to set and to reset. Exclusive or, a register A or B with any operand. Anything you do an exclusive or with is what? An XOR, basically. Exclusive or. If you want to do something, you can imagine one of the inputs is the input, right? And the other bit that could be the control. If you make it a 0, then you're passing the input as is, right? Anything you XOR with 0, then you're just doing like a buffer, right? Buffer. If you XOR with a 1, you're doing what?
Inverter.
An inverter. Yani, if you want to flip bits, you XOR them with 1. If you want to keep them, you XOR them with zeros. These are the XOR, EOR. Clear condition bits, carry flag, clear interrupt flag, clear the V flag, clear com is do the ones complement for a memory location, ones complement for A and B. Ones complement is flips all bits, right? Negate is ones complement plus 1, yani two's complement. It takes the negative number of it. You can do it for A, B, or a memory location. These are the Boolean logical instructions. And these are all bitwise for the AND or XOR. So every bit by bitwise, okay? And these are equivalent in C to the single AND or, right? So in C, you say, if you have A equals to $AA and B equals $55, if you do if, what do you do? If A and B do this one, else do 2, right? In this case, if these are the values of A and B, what will happen? What will be the condition here? Is it going to be true or false? Is 1 is going to execute or 2?
هون 1 راح يكون.
A is true and B is true, right?
True.
This is a logical AND. We call this a logical AND, right? Logical AND. If you do if A and B, do 1, else do 2. This is a bitwise AND, just like the ones in assembly we just saw, right? A bitwise will do check every bit against the other. I'm done, guys. I'm going to close it for those who are late to other class. So A and with 55 and will result in a 1010, 1010, and with 55 0101 0101 the result is 0, 0, 0, 0, 0, 0, 0, 0, right? It will be false. And here, this is the one that is going to execute. Here, this is the one that is going to execute. Talking about our logical instructions here, here are bitwise, just like using the single ampersand or the single or. Okay. Okay, we're done here. Next time, we're going to start talking about program execution time, e-clock. What is the e-clock? How do you compute time? Hopefully, we'll finish all these things, assembly stuff and timing next lecture. If you have any questions, you may stay until I stop recording. Thank you very much. See you Wednesday at 3:30.